one. So this is, for example, the first line, and the second line, for example, like this one. So the result is not clear, and the road is not clear. So any small change, for example, if I move this one, for example, from here to this point, for example, if I have any change, this will produce a large change in the output. Okay, this will produce a large change in the output. So as a result of this one, so we need to deal with this carefully. Okay, so one method to avoid the zeros buffet element, if the buffet element is zero or the buffet element is very, very small, because we have two cases. Otherwise, buffet element is zero, so I cannot divide it, because to eliminate this coefficient, I have to uh, use this coefficient, for example, for the second row and divide this over the buffed element. So in this case, to eliminate the x from the second row. So to avoid this one, we need to use Newt methods. We have two methods here that we use it. One of them we call this, we reviewed in the previous lecture. We call this Gaussian elimination with buffeting elements, or with partial buffeting. So in this case, in this method, what we study here, we compare the coefficients of the matrix. If we have the system of the matrix, we look for the maximum value in the first column. Here, for example, maximum magnitude. Okay, maximum magnitude. So here, this is I have four rows here. So just I look for the magnitude. Okay, so we need to find the maximum magnitude. So after that, I will compare. So for example, in this example, this is easy because I have zeros here. Okay, this 0 and this 0. So I will compare this one. I take the magnitude of this 0 or 2 and magnitude of 1. So the maximum magnitude in the first column, because here the first step we want to eliminate x1. This is the first step. I want to eliminate x1. So I look for the maximum magnitude in the first column to eliminate x1. So here, for example, we find this the maximum magnitude. So if this is the maximum magnitude, so this I will interchange this one, or change this one, or swap this one with the first row. So this now becomes a buffet row. The second row becomes the buffet row, and row 1 will return back to this place. So we have swapping now between the rows. After that, we apply the elimination like what we have before. Okay, for the first, we complete the elimination to make the coefficient in the first column below the diagonal are zeros. This is the diagonal here. So below the diagonal, this should be zeros. So this is the first step, as we said, using Gaussian elimination with the partial buffet. Because we use here partial buffet, we take only one column. So in this case, we find this is the maximum magnitude. So in this case, we'll do swapping. This now becomes the buffed element, or the buffed row, pi. Okay, and this become the buffed element now. The buffed element. So after that, what we do now, Gaussian elimination. That we did before. Naive Gaussian elimination, we just cancel this to make this 0. I want to convert this coefficient now to 0 by using the buffed row. Okay, by using the buffed row. That means I multiply this one. So I will take the ratio, or the this one 0 or 2 over the buffed element. This one. I multiply this by row 1. The new row 1. Okay, and I will subtract this one from row number, or the buffed row, after that to make this 0. Okay, so if we do this one, so you'll have to change in these coefficients. So the first row will not change because this is buffed. So as a result, I will have change in the coefficients in these rows. So for example, this row number 1. Okay, this will change, this will change, this will change, like what we have here. So after that, I will look for this one. If I need to do elimination, more elimination. So for example, if I have here a number 1 also, or 0.1 or anything. So also I want to do elimination for this element to make it 0, or to convert this to 0. Because here these already zeros, so no need for more eliminations here. So now we have x1, we can find it because only we have this one and the others are zeros below the diagonal. So now we want the next step to eliminate the coefficient of x2. And the coefficient of x2, this is already buffed, so no need to change this one or introduce this in our calculation. Okay, so this is now the step after we do the second elimination. This is after we do elimination for this one. For the first one, we get this one. Okay, so now we take also, because now we're looking for x2. We want to eliminate x2 now from the matrix. So we take here the comparison in the second column, not the first column, now in the second column. So this also should be included, but this because of 0, I take it out. Okay, so we need here to take the magnitude of this one. I have here 1 and this is 0.03. So in this case, we try to find the new buffed element. So if I take the compute the magnitude here, I will find this one is the maximum. So in this case, this should be the next buffed row. And this I have to do swap in here. So this will be the new criteria, the next step. So the next step is to eliminate x2. Now we do an elimination to x2. So in this case, I find this will be the second buffed element now, or second buffed row, and this will be the second buffed element. This buffed element that I will use it for elimination below the diagonal, and this is the second buffed row. So the buffed row, that means unchanged. We cannot change this one. We fix this one because we do elimination based on this element in these rows. So as a result here, what we do, so you want to eliminate the coefficients below the diagonal. This is the diagonal here, and so we have only one coefficient. So again, we do elimination for this one by using this coefficient. So I multiply by 0.3 over 1 multiply by the row number 2. So I take a coefficient of R3 multiply by the ratio between the coefficient in the second, the third row, the second column, over the buffed element, the second buffed element, multiply by the row 2, because this is the buff that we use it here. I subtract this one from row 3 because I need to eliminate the coefficient now in row 3. So this coefficient will not change because here we multiply this by zeros at this time. So this will not, we don't have any changes here. So change will be here. So if we do this one, we use this buffed row now, we get this now. After that, we get these 2 zeros here. So if we go with the diagonal here, we see that we still have one coefficient to eliminate is 100 here. So now to do elimination in the third row, this already buffed and this already buffed, so no change need for this one. I will not include this in my calculation. So now I will compare row number 3 and row number 4. I will look for the maximum magnitude. After that, I will consider this will be the third buffed row. So as a result, if you compare the magnitude of 0.04 with 100, so I will consider this will be the maximum now. So this will swap between row number 4 and row number 3. So this will be the new buff that I'll use it. So no change will happen to this one because no change we want to do it for these buffed rows that we have it before. So this 100 now, the second buff. So to eliminate this one, so what I will use R4, the old one, it's minus, the ratio here is 0.04 over 100. Multiply this by R3. So I have here this is R4. I want to cancel this coefficient. So I multiply by 0.04 over 100 multiplied by I3. So in this coefficient, I will get this 0. Now the matrix becomes upper triangle matrix. It is easy to use back substitute. So it is easy to get x4 from this element because x4 will equal the ratio between minus O2 over minus O5. Okay, so in this case I will get x4 and then x3 and then x2 and lastly will be x1. Okay, so this one we can see this is the steps. We get x4 here, and after that we have x2, 3, x2, and x1, and we said we can see that we do here back substitute like what we have in the Gaussian elimination. So this buffeting element usually it helps us to reduce the errors, because of if we have the buffed element is very small when compared to the others. So this will reduce the round of errors and enhance the accuracy during this calculation. Any question here, Yashaba?
Yes, Doctor. For the previous slide, please.
Okay, welcome.
The third row, it's 100. Should we make it the coefficient to 1, or we don't need?
No. Here we don't use any skill for the factors. No need for divided this over 100.
No skill, no change.
Yes,
because okay.
Yes.
Because of what?
This is the method. This usually, as we said in the previous lecture, this usually is algorithms. No need for this method is numerical methods. It's algorithms. I will show you inshallah. Next slide.
Mean we have to follow the logarithm itself?
Yeah, algorithms only. Okay, so we have algorithms. I will share with you inshallah the codes of this one. I will have one class inshallah this week or week after to have one class just to review the algorithms that we did before. So we'll try to have, because the problem that I use MATLAB here from the university, so it is I cannot download the package, any package or tools, until I get permission from ITC. So in this case, I want to request help from ITC to give me a promotion, or they would download the tools here. Okay, for in my MATLAB. After that, I will show you how we can do this one, or we can do algorithms, but algorithms will take more time. But I want to, I will show you the algorithm. After that, we'll discuss how we run this or how we can implement the codes in different language that might you use. Okay, so this is just about this course, just algorithms. Numerical method, that means we use computational methods, algorithms that's developed. The codes for this one I haven't, but if I need to download the tools, I cannot. Okay, so this is the reason now. I tried, but I cannot. So inshallah, I will get help during the office hour to download the tools that I want, and inshallah this week or at the beginning of next week, I will prepare. I will tell you we have tutorial, one class or half of the class, to have review or introduction to MATLABs. We'll review the codes that we have before. Okay, may also work with you on the homework that you have. Okay, any question until here? Okay, this method, ya shabab. This is partial skill. We have two methods, inshallah, we'll study. Please distinguish between the two methods. This is partial skill. This is, sorry, partial buffet. And next method we'll study, we have skilled buffet. Okay, skilled buffet, that we have to find the maximum in each row. And after that, we compare this with the buffed element in the first column, and then in the second column, and then in the third column. We'll see inshallah next slide. Any question here for the first method? Okay, so this method should be better than the Naive elimination and Gaussian elimination, because it reduces the problems or the pitfalls of the Naive eliminations. But also, so let's take this example, the benefit of the partial buffeting. Okay, buffeting here. So if we look for this one, if we use this is here comparison between partial buffeting and Gaussian elimination, that means Naive elimination without any buffet. Okay, if you look for this one, this coefficient now, because if we use Gaussian elimination or Naive Gaussian elimination, you'll see this should be the buffet element. Okay, this buffet element, because in the Gauss and Naive elimination we consider the first coefficient in the first row, in the first column, this will be the fifth element. After that, we use this one to eliminate the coefficient below the diagonal. Okay, so here, because I have this one is very, very small, so by using Gaussian elimination, so what we do, so we multiply the first row, this is the first row, I multiply this by 1 over 0 over 3, sorry, and this minus R2, or R2 minus this coefficient. So we multiply the first equation by 1 over 0.003. Okay, so this will give us this new coefficient of R1. After that, we subtract R2 from this one to eliminate X1 from the equation. As a result, after we do this elimination, we'll get X2 equal 6,666 over 9,999, this equation. So in this result, we'll find that if we solve this one, we'll get this is X2 and this will be X1. Okay, and here, because of the subtracting cancellation, we do some cancellation here, and the parameter here is very, very sensitive to the number of significant figures. So this is the results here that we have. If we consider, for example, 3 significant figure or 4 significant figure or 5 significant figure, this will be the solution now. This is our estimate or solution of X2, and this is of X1. But here, if you look, ya shabab, for the percentage relative error for X1, if we compare this with X1, okay, so when we use 3 significant figures, you will see that the error with respect to X1 is 1099. You can see this is very, very huge error. Okay, because the problem that the value of X1 or the buffed element is very, very small. If we use 4 significant figures, so you can see we have very, very sensitive computation here. If we do here, for example, we increase only significant figure by 1, so the error will reduce it to 100. If we have 3 or 5 significant figures, so this will be 1 like this. Okay, so the result here is very, very sensitive to the number of significant figures that we use it in our solution. This table shows us what will be the pitfalls of the Gaussian elimination or Naive Gaussian elimination if we apply it directly without doing any reversing of the rows, like for example partial buffed elimination. Okay, so and this is the exact solution here. So let's see this one. This is the exact solution we should know. X1 is 1 over 3 and X2 is 2 over 3. After that, ya shabab, if we use, for example, buffed or partial buffed in here, okay, and we said the solution of X1 is highly dependent on the number of the significant figure. So if we do partial buffing, so we have to do swapping here, because if we return back to the problem, I have to compare the maximum magnitude of this coefficient and the maximum magnitude of this coefficient, because this is larger than this one. So I will have to do swapping. This will be the buffed now, and this will be returned back to 0. After that, this is easy to eliminate this one. So we'll get this coefficient. After that, I have to convert this to 0 by using Gaussian elimination. That means I will multiply 0.003 over 1, 0, 0, 0, 0. Okay, this multiplied by R1, the new R1. This now R1, and this is subtract from R2. As a result, no change will happen to the value of X2. We'll get the same result, but the difference, we'll see that if we do this one with the partial buffing, we'll see the error. If we use 3 significant figure, the error is very, very small if you compare this with the Naive elimination, because there we have around 1099, and here we have only 0.1% error. And here, if we use 4 significant figures, so the error will reduce nicely. We have a nice results here if we compare this with the same, if we apply different algorithms on the same problem, okay, without considering the effect of the buffet on the solution. Any question, Shabab, here? This example, it shows us how important that we use partial buffeting. Okay, partial buffeting is very important. We can do this using our algorithms. Okay, our algorithms, we might, for example, take the max. If this is the matrix, for example, you have matrix here. So this is the matrix. This I will include all the rows, and let's take this one. Should be like this one. For the rows, for example, the first column, the first one, and after that I will decide. This is will take the maximum magnitude or absolute value, the maximum absolute value in the matrix, for example, A. This that means all the rows, and this one to represent the first column. After that, I will compare the coefficient in the first column, and then, for example, I will select this to be the buffet element. I will interchange this one with the first one. After that, we do cancellation. Okay, so and usually in the codes, for example, in our tools like MATLAB, we have already packages or tools, for example, to do the Gaussian elimination. So we need only to do normalize for the equation or for the system of the equation. After that, we do elimination directly. Okay, so the first step, and next step also we consider the buffeting for the second column, and then, for example, for the third column. Okay, so this partial buffeting, it solves one of the major problems. If we have the coefficient is 0, or the buffet element is 0, or the buffet element is very, very small, if we compare this with the same and with other elements in the same column. But sometimes, ya shabab, if we do the partial buffet, it's not also it can cause some errors. We need to have more advanced method. It's not that huge error, but a little bit. Yani, if you compare this with the Naive elimination. Okay, so one problem. Let's show this one. Here, for example, if we use partial buffet, okay, and this one here you have 100 or 10, and this is 1, and this is 1, and let's take this x1 here, and this x2. Okay, this -1, for example. Here, for example, in this row, I have here, for example, this is power 10, and this here power 10. If we do here partial buffeting here directly, because we take because here I have 2 rows, 2 by 2 matrix, so that means we need only one step for elimination. I want to eliminate this one below the diagonal. So in this case, if I do this one, I will, for elimination x1, I will take here the maximum magnitude of the coefficient in the first column. I will do comparison between. Okay, even if this is negative, so like this one, so the maximum magnitude here, this will be 10. So in this case, this will be the buffed element. But actually, ya shabab, if we look for the scale or the ratio between the 10 here with the others numbers here, for example, this is 10, but here this is a 10 of power 10. Here we have here 10 also of power 10. So that means this coefficient, if we compare with the other coefficient in the same equation, this is very, very small, and it is equal to 0 almost. Okay, near to 0. So in this case, by using partial buffeting here, elimination, so we will select this one. So to minimize the errors that it can be caused because of the round of errors, because here this is, if we do scale for this equation, this will be around 0. If we round off this error, this number to 0, so in this case we'll get, for example, some round of errors. So one techniques to improve our solution, to improve the accuracy that we have, it is by use a scale. Why we do a scale? So we compare this buffet with the maximum magnitude in the same row. I will not consider this as a buffed with respect to the coefficient in the first column only. No, I have to compare this with the coefficients in the same row. Okay, so I will compare this with the coefficient here. So that means I will take ratio 100 over L1 of 10. I will compare also this one over 1. I will see what will be the maximum here. Okay, so this one over, what's the maximum magnitude in the row? So the maximum magnitude in the row is 10 of power 10. So this will be my scale. The maximum scale in this row, number 1. After that, I will take ratio between the buffed element or the element in the first column over the maximum magnitude in this row. So this one, now this is the ratio of the first row, and also I will take ratio for the second row. So the ratio of the second row, that means the maximum magnitude in this row. So assume this is 1.1. So the maximum magnitude in this row is 1.1. And the buffed element of this row, or the element in the first column of this row is 1. So I take ratio 1 over the scaled element. So this will be, if I compare this ratio between 10 over 10 power 10 with 1 over 1.1, so I find this ratio is greater than this one. So in this case, we consider this one with the maximum ratio as the buffed row now, not this one. Okay. The other advantage of the scaled method, no need to do swapping here, no need to interchange, to do swapping between the rows. Why no need? Because here in this method, we will use something called index vector. So we have index vector that's have index of the location of the rows. So here, for example, this index vector, we develop it from the beginning. If we consider, for example, R2 is the buffed row now, so I have to interchange between the index numbers, not the rows. So we have to change with the index only. Okay, so we do change with the index, no need to do swapping in the matrices. So this also will simplify the solution and the algorithms and make the process faster, because no need to do swapping between the rows. So we just continue elimination using Gaussian elimination. Okay, so this is the new method, Gaussian elimination with scale partial buffet. So in this method, as we said, scaled partial buffet, place the element in the buffed position that will be largest relative to the entire in its row. So we have here this the buffed element. That means if I want to cancel x1, so this we call this the buffed position, the coefficient in the first column. So in this case, we place the element in the buffed position, so the first column, because now we are doing cancellation to x1. That's the largest relative to the entire in its row. So we look for the maximum in this row. What's the maximum value in the row number 1? So we build something called the scale vector. We take this one. So for example, I have here 10. So this will be the maximum magnitude, and the first one will be 10. Okay, in the scale vector. I will take also the maximum in the second row, the maximum in the third row, the maximum in the fourth row, like this one. After that, to cancel this one, I will take a ratio between the elements in the buffet position with respect to the maximum scale. So which row that have or has the maximum ratio, in this case, this will be the new buffet. We'll do the same for x2. So x2 now, if we do x2, we look for the coefficient in x2. So this now will be the buffed position now for x2, not this one, because this only for x1. After the first step, this should be zeros. Okay, we have zeros here in the first column. We have only one coefficient. We'll do this for the second row, for the third row, like this one. So at each step, we have to select the buffed element. Okay, and we do ratio. Let's take example. This will be clear. Okay, so this example that I have, we in our calculation, يا شباب, we have some mistakes. You will see here we have 2, and after that here we'll have it 3. Okay, please double check with me. Okay, this one. I will revise this inshallah later. Okay, so here solve the following system using Gaussian elimination with skill partial buffed. Okay, so that mean here what we want to do is to generate or create the first step, what we call this the index vector. The index vector, we index the coefficients here. So we create something index vector. So this we call this L index vector. I have just indexing of the rows that I have. So for example, at the first position now, I have row 1 in the its position, row 2 in its position, row 3 in its position, row 4 in its position. Why we need this one? We need this index vector here. This will help us to have change in the index vector. If I do swapping here, I will do the swapping between the indexing, not between the rows. So if I decide, for example, this is now row number 2 is the fifth row, I have to swap it, for example, to be number 1. So by using this index vector, no need to do swapping between the rows. I just do swapping here between this coefficient and the index. Okay, so the new matrix will be 1, 2, 1, 3, 4, like this. So I just do swapping in the index vector. No need to do swapping in the calculation. That will make the logarithm more faster. Okay, so it is easy here to do swapping in the index vector and still to do swapping in the matrix by itself, because sometimes the matrix will be 100 by 100 or 1000 by 1000, so it's need more computation. Okay, so this one, what's the need of the index vector here? This will be the difference between the skilled and partial buffed. Here no need to do swapping between the rows. Okay, no need. The second step is to generate the skilled vector. The skilled vector, ya shabab, this, as we said, this will be the largest magnitude in each row. So for example, this is the row, the first row, 1, minus 1, 2, and 1. So here I will look for the maximum magnitude in the first row. If it is negative or positive, here we take the absolute value, the magnitude only. So here, for example, in row number 1, I have the maximum magnitude is 2. In row number 2, I have 3, 4, 1, 4. So this will be 4. And the third row, I have 5, 8, 6, 3. The maximum magnitude is 8 for the row number 3. And the fourth row, I have 4, 2, 5, 3. So the maximum will be 5. Okay, so now we generate the skilled vector, and that we have here the index vector. What we rest, we do a ratio now. We will do ratio between these coefficients. So why we use the index here? We use the index because it is very easy to interchange a single index element. Would compare this with interchanging the values of the complete row. Okay, so it will be a practical problem in very large in elements. For example, if we have a huge matrix, we need to do interchange between the rows, so this will take more time. So it is easy to do this one using indexing. So here, Yashiba, what we do, we have here the first step to do elimination. So the first elimination is to eliminate x1. We start with x1. So to eliminate x1, we already have this, the skill matrix or skill vector, and we have here the index vector. And we said this is the maximum in each row. So this 2 is the max in this row. And this is the max in this row. And 8 is the maximum in this third row. And 5 is the maximum in this row. After that, we need to compute ratio. We want to compare, because now I am doing elimination for x1. If I do an elimination for x1, so this is represent x1. The first column only, that's represent x1. Okay, so if I do an elimination now x1, I will consider the coefficient now for x1, the first column. Okay, that means the first column only. So what we do now, we have to take ratio between the coefficient in the buffet position with respect to the scale. So the maximum magnitude or the maximum ratio, this will consider, or the row that has the maximum ratio, this will consider to be the first buffet equation. So here, for example, if I take the coefficient now, I have 1 in the first row, and the scale of the first row is 2. So I will take 1 over 2. The magnitude now 1 over 2. So this will be the first one, 1 over 2. For the second row, I have 3, and this 3 over the maximum scale, this will be 4. So I have here 4. For the third row, I have the position here for the coefficient in the first column for the third row is 5, and this will be over the maximum in this row, this will be 8. Okay, and for the fourth row, I have 4 here in the first column. I will take ratio with respect to 5. After that, we look for the maximum magnitude. We just use our calculator to compare these values. Okay. So, for example, here I have here this is 0.5, and this, for example, 0.75, and this, for example, 0.62, almost 5, and this, for example, 0.8. So this coefficient is larger than the others. And this, you can see, this is represented line number 4. So this is the ratio of line number 4. So in this case, what we do, just we fix this at its position. Now this is the buffet, our buffet element here. Buffet here. Okay, this is the buffet equation. So what we do, just I will change the index vector. No change will happen to the matrix. I will do no change in the index vector. That means I will change now. Before I have 1, 2, 3, 4. So I will do swapping between these two. Okay, I will do swapping. So now becomes 4, 2, 3, 1. Because this will help us later how we do back substitute. Okay, Shabab. So this is it's clear, Shabab, here. What's the difference between the skilled and partial buffet? Any question, Shabab?
Why we exchange 4 and 1?
Okay, this one, because here we want to determine the first buffet equation. What will be the first buffet equation? Before, in the previous equation, if we consider this, for example, here, this is the buffet, or the buffet equation, or the buffet line that we determine. How determine this? We take the ratio between the coefficient in the first column, this is 4, over the maximum magnitude in this row. Okay, we compute ratios. So here, for example, because we do an elimination for x1, so here I have 4 over the maximum ratio, or the maximum magnitude in this row is 5. So this is 4 over 5 for the first row. We find that this ratio of line 5, or row number 5, row number 4 is the maximum magnitude, or the maximum value. We compare with the others. So here we select this row number 4 as the first buffet equation. So this now, row number 4 will be my first buffet equation. Before, in the previous method, what we do? We do swapping يا شباب صح between rows. لو رجعنا هنا, if we return back to this one, if I, for example, went to, let's say, for the first column, here, for example, if we want to do elimination, here, for example, I compare this one magnitude and this magnitude, and I find this L1 is larger than this coefficient. So what I do swapping between the rows. So this I move it, for example, to be row number 1, or no, row number 2 becomes row number 1. And row number 1 return back to become row number 2. So we do swapping between the rows. this in the previous in the partial BIFT and also in the partial BIFT. Yeah, in NIF we just apply direct substitute elimination. Here what we do, no need, for example, to do swapping between the rows. We just change the index vector that we have. This is the index vector that we have. So this is the location now of row number 1, a location of row number 2, a location of row number 3, a location of the original row number 4. So this index skill, instead to have swapping between the rows or interchange between the rows in the system of matrix, just we do this swapping or interchange in this small vector. So just we eliminate here without any interchange or swapping between the rows. Clear?
Here.
Okay, so here we just change now, because here is we select row number 4 to be the BIFT equation. So we interchange between row number 4 and row number 2. So just I replace this one by this one. Okay, so now I have 4, 3, 4, 2, 3, 1. So at the end we'll solve from this one, from the back. We'll see later. So if we do this one, now we determine this one. So we have to eliminate the coefficient now above in this row. Okay, this row, for example, I have to convert this one to 0, convert this one to 0, convert the 5 to 0 by using this row, like the Gaussian elimination, what we do before. So here, for example, يا شباب, we use this BIFT equation, BIFT equation here to do these eliminations. Okay, to do this elimination. If we use this one, this row is BIFT, so that means I multiply, for example, to eliminate this coefficient or this coefficient, I will take a ratio, for example, here to eliminate the coefficient and row number 1. Let's do row number 1 first. So row number 1, this will equal row number 1 minus. Okay, so what we have here? Here we have a coefficient is 1 over 4. Okay, the coefficient is 1 and the BIFT element is 4. So this will be multiply 1 over 4 multiply by row number 4. Okay, so this one. So that means I want to convert this one to 0. Okay, as a result, if I have this, for example, row number 1, if I type here row number 1, the original one, so this is sorry, this is 1, we have minus 1, 2 and 1, and this should equal 1. Okay, not forget this one. So if I multiply, this is minus 1 over 4 multiplied by R4. Okay, that means I multiply 0 to 5. Okay, so the result here, this should be 1. Here, for example, this should be 1. And second coefficient should be 0.25. If this one also, the third one, 1.25. What about the third, يا شباب? This should be how much? Okay. 0.275. Okay. I've clicked this one, and the last one minus 0.25. Okay, so after that we do subtract here. So I do subtract here. This the first element should goes to 0. Okay, and this should be, because if we cancel this one, so minus 1 minus 0.5, so this will be minus 1.5. Here I have 2 minus 1.5, so this will be 0.07. 5. I have here, this is 1 minus 0.75, so this should be 0.25. Here I have 1 minus 0.25, so this will be 1.25. So this is the result of the first row, this one. Okay, so here the first column, the first one 0, the second one is minus 1.5. I have here 0.75, this is 0.25, and here the piece will be 1.25. Okay, so this we do the elimination for the first one. Now we finish from this one now. So we already eliminate the coefficient for the unknowns x1. The first step is done now. What the next step? We need to eliminate the coefficient in the second column. But here also we need to use these coefficients that's considered, because we want the next step to do elimination to x2, we need to use this position, these elements that's located in the buffet position for x2 to find the new buffet row, okay, or buffet equation. So the next step or step number 2 for forward elimination, we eliminate x2. So in this case, because we eliminate x2, so here also we need to look for the ratios. The same thing is what we did before, but now we look for the second column. As we said يا شباب, هذا الفورت row خلاص we fix this one. No need to consider this in our calculation because this is unchangeable. No need to do any elimination to this row, and also this should be fixed. Okay, so here يا شباب the scaled factor يا شباب we use it the same. هذا scaled factor we determine from the beginning of the equation. This is the scaled factor, but this should be changed. Okay, this is changed. This is the scaled factor. This is the maximum in the first original row number 1, and this is the maximum in the original row 2, and this is the maximum row 3, and this is the maximum in row 4. So we need to compare now, because here I have only row number 1 and row number 2 and row number 4. So we take the ratio. So for row number 1, I have now the element in the buffet position is I will take 1.5. So I will take the absolute value over, in the scaled factor I have 2. For row number 2, I will look now for coefficient in the row number 2 is 0.5. Okay, so 0.5 here. Okay, and this should be over the scaled will be 4. And here, for example, row number 3, I have 5.5 over 8. Okay, so here, because the maximum in the original row for row number 3 is 8, so the scaled factor will goes with us. So this is what we have here. Okay, شباب, clear this step? We compute the ratios now for the second row. We need to find the second buffet equation. We use now the coefficient that's located in the second column. We expect يعني not use the first buffet. We use the other elements here. So we take the ratio between this coefficient with it is scaled, maximum scaled. Okay, so we take this one. If we consider this one, we'll find this one will be the maximum ratio. And these represent row number 1. If we look for the briefest index vector, and the briefest index vector, if I assume this is for the first iteration, we interchange between 4 and 1. So the index vector becomes 2, 4, 3, 4, 2, 3, 1. And now, because I find that the second buffet equation now is row number 1, so I will do swapping between the index of row number 1 and row number 2 as a result. So this will be the second iteration. Okay, in the second iteration I will get 4, 1, 3, 2. Okay, that means this will be buffed now, will not change anymore. So I need to eliminate these coefficients. That means I will convert this one, this coefficient 0.5 to 0. I will convert also 5.5 to 0. Clear يا شباب؟
Dixon.
Yes.
Here I will consider this the biggest one. I will not consider the second one when I do swap.
Which one? Yeah. You talk about.
For example, here, if it is index 4, 1, 2, 3.
Yes.
After we do the comparison, it will be 4, 1. Sorry, 4, 2, 1, 3.
No, because here, as you know, here we do this step, second alteration. We want to put the index now, what will be the second buffed element. So we look for this position. Okay, so we look for the index in this position now, the second buffed. Okay.
I will not care about the rest.
Which one?
I mean the rest, I consider it as أهتم
Yes.
البقية أو
Just we do swap. Here we do swap. يعني swapping أنت وجدت إن ال x1 or row number 1 is the buffed now. This bi. هذا already bi. هذا not fixed. هذا خلاص ستار. ما تتغير. This will not change. Okay. ال 4 will not change. هذا خلاص انتهينا من هذا ال 4. We'll take the first position. هذا خلاص جاب الدراجة الأول ووصل. أول واحد وصل في السباق. Okay. بعد ذلك we'll compare this one. We'll do ratios. We'll compare ratio. هذا this is the first. For the first iteration I have this the index vector. But now, for example, after the first step, I found row number 1 is the second, should be the second index, should be the second buffed. Then row number 1 now should be the second buffed. So this R1 will interchange with this row. يصير swap between them. هو ما يشحق نفسه كده مثلا ما نقول يعني ما نكتب كده مثلا نقول 1 2 3 يعني just we give him space. Okay, it comes between these two. No, we have to do swapping. A 3 will stay at its position. You get the point? No need
Yes.
يعني no need to do swapping in the matrix before we نسوي swapping here or interchange in the rows. We put this at the top and after that we have to put this here like this one. So no, here we have to interchange completely. So this will take the position of row number 2 and row number 2 have to return back to the position of row number 1. Okay, have to. Yes, so now this will be buffed here and this now is buffed. So this will not change anymore. So now still we have يعني here fighting between these two rows. What will be the third one? Okay, what will be the third one? So again, يا شباب, if we do this one, I have to change the skill. Skill will not change. I have to change only the index vector. Okay, I will do elimination now. So this is now is the second buffed equation. That means this will not change it. But if this you select this buffed, so that means it will not change the coefficient now. So what I want to cancel this one to make it 0, and also this 5.5 to be 0. So this is the same thing as what we did here. Okay, the same things. This the indexing for the rows. This is the original one. Okay, so this is the index and this is the original one. We have it, and this is the ratio. And because this is now row number 1 is the second buffed, so we put it here. We interchange here. So what we do now, if you want to do the coefficient now to eliminate this coefficient, I will not use this too. No, this is wrong. I will not use this one. The row this I will not use it, so I have to use the second buffed equation. The second buffed equation. Okay. So what will be the buffed element of the second for the second column? This will be. So I will use this coefficient now to eliminate these coefficients 0.5 and 5.5. Okay, so this is the first buffed, or the buffed element for the first row. So this is the second buffed equation. After that, this is the index, the new index for the second iteration. So we use this coefficient. Okay, that means if I want to eliminate this one, so I have row number 2 minus row number 1 multiply by the ratio. Ratio here we have the coefficient now is 0.5. Okay, 0.5 here over what is we have it here
minus 1.5.
To eliminate this coefficient.
Yes.
Which one?
0.5.
1.5.
1.5. Okay, so we do elimination. So we multiply this one. After that, yes.
Isn't minus 1.5? Because when I do the subtraction, not to be addition.
Yes, this one, yeah, this should be minus, yeah. Minus, yeah, sorry. This will be,
Yes.
yes, this coefficient over this coefficient. Okay, so we take this one. So in this case, if we do this one, so we'll have this should be 5 here. Okay, because we want to eliminate this coefficient for the second row. Okay, this for the second row, so we use this one. So, and this result, as a result of this one, the first element should be 0.5 here. So the second element, because this will be 0. For this one will not change because we multiply here by zeros. Okay, this will not have any change here. Okay, this multiply by 0 and subtract from 0, so this will be 0. So we have change here in this coefficient. So this becomes eliminate this to 0. So I will have change in this coefficient for the entire one. So this will not change anymore because this is unchangeable and this is unchangeable as well. So now we do elimination here for this step. The second step, we eliminate x2. So still we have one coefficient, one more to eliminate because we look for upper diagonal like this one. So that means I need to eliminate one coefficient. Okay. So here, for doing this one, what we need. So now the next step, we want to eliminate x3, the unknown x3. So for this case, we look only for the third row or the third column. هذا يا شباب قلنا this is one is buffed because this is buffed is unchanged, so I will not do any change to this coefficient. This also it is located in the buffed, the first buffed, so no need to do any change here. So what rests with me is these rows. So I have to compare between these two, row number 2 and row number 3. I will select what will be the third buffed equation. This already buffed, this already buffed. Okay, A plus will A, B plus. Okay, so here we want to select what will be the third buffed equation here. So we'll do ratio. I will take this one, ratio of this element in the buffed position of x3 with respect to the scaled vector that we have it from the beginning. Okay, so here I have this is the magnitude minus 2, 5, magnitude minus 2, 5 over the maximum in the original or from the scale. This is the scale from the original. The maximum for the original R3 is 8. So I will take this 2.5 over 8. For row number 2, row number 2, this is row number 2. This should be 0.5, yeah. It's 0.25. Okay, this 0.25 should be, yes, this 0.25 or 5. Yes, 0.25. This 0.25. Let's take this one.
No, it's 0.25 over 8.
No, this for 3. Yeah, 0.25 over 8, sorry. this is 43, yeah, this is 0.25. And this is 25, thank you. Okay. ملخبط أنا لسه. This one. This is for row number 3, sorry, sure. This is row number 3 is 0.25 over 8. And here we have minus 25 over 4. This for x2 for original row number 2. If we compare these two ratios now, el 0.25 over 8 with the 2.5 over 8, so I'll find this will be the max. And this is related to row number 2. So in this case, just I will change. Okay, I will do change now. Before, in the second iteration, we have 4132. So now I have to change between the 2 and 3. So this becomes 4123. Okay. So also this now the second, this buffed and this buffed equation. This number 1, this is the second, and this is the third. So that means I want to cancel this coefficient now to make this 0. Okay, to make this 0, I will use Gaussian elimination, but I will use the help of the second row. I will not use the first buffed equation, or I will not use the second buffed. I will use the third buffed for this step. So we'll do elimination to get this 0, so we'll get this result. Okay, if you do elimination here for these columns, because this is buffed here, so we do elimination to get this one. So we can see, Shabab, it is now easy to solve. What we change, we just change the index vector. After that, we apply a back substitute. A back substitute here, Shabab, we follow the index vector. You can see the index. The index, you start from row number 3. Told you this one. The solution will start from here. This is back substitute. Okay, index vector tell us that we need to start from row number 3. I will find, because x3 here is equal 9 over 2. If I find this one, I will compute x2 here, and then I will compute x1, and finally I will return that back to x4. Okay, so this is a logarithms here. We need to adjust. Okay, so we do elimination like this. Any question here, ya shabab? Any question? If I give you a problem like this one, the first step you have to distinguish between the two methods, the partial, buffed, and the buffed itself. Okay, we might have question, for example, to do comparison or to solve this one. Usually we have problems like this. And also what we have in the sample method, like Naive equation, we compare this with this method. Any question? So what's the benefit of the buffed equation or the scale buffed equation? We compare this with buffed equation without scale. So this we have here. So for example, we can see we have here comparison in this example. Okay, this example chapter 9, example number 10. This here comparison between Gaussian elimination with scaled buffeting or scaled with buffeting without scale. So we use this example, as we said, sometimes, because if we use scaled, buffeting without scaled, so I will select this one directly because 2 is greater than 1. So this will be my first buffed element. So in this case, this will be my buffed equation. As a result, I will do elimination based on this one. But in the scaled one, we need to take the maximum in this row. This will be 100,000. And after that, we compare the buffed element with this ratio, in this ratio. So in the scaled, this will be the first buffed equation. So as a result, يا شباب, if we compare these two methods here, for example, in this example, so here, what's the true values that we have? If we use here only 3 significant figure for this solution, and we find that, for example, the correct answer for x1 is 10002, and the correct answer for 2 is 0.9998. Okay, so for a 3 significant figure, we'll find that x1 is equal 1 and x2 is equal to. So 3 significant figure with rounded. Okay, with the round here, I will find both is equal 1. So without scaling, we solve this one, but without scaling, if we do buffeting without scaling, buffeting only. Okay, if you do buffeting only without scale, you can see that mean if I solve this one by doing elimination, I select this is the buffet. After that, I cancel this one. I will find x2, this is correct, and find x1, this equals 0. x1 is 0. So although x2 is correct, but x1 is 100% error. We have here 100% error if we use round off. Okay, because if we use round off, we get these ones. This is the correct. But here, this is 0 here. If we use Gaussian elimination with scale, okay, so we solve this one, and if we scale the equation, after that we do elimination here, forward elimination. So as a result, we find that this will be the solution here. Okay, so here the correct answer, what we have. So here by using the scaled method, we find that the correct answer, the end error is 0. Okay, and the error is 0. So we find that also scaled partial buffeting, it is help us to reduce the round of error. More advanced, it need more steps, more complicated, but as a result we can get good accuracy. Any method that it has, for example, advantage and disadvantage like this one. Okay, but the skills should provide a better solution or better accuracy if we compare this with others. In some equation, they give us the same. One benefit of the scaled one, we use here the index vector to avoid the need of the moving of the rows. Okay, because the moving of the rows in the large systems, this is very difficult or more complex. Any question, Shabab? Else.